Let's graph the inequality 2x greater than 3y. The first thing we'll want to do is to graph the line that is associated with this. So 2x equal to 3y. The easiest way to do this one is to go ahead and put it in slope-intercept form. And so that will give me 2/3 x equals y, and I rearrange a little bit and I get y equals 2/3 x plus 0. So my slope is positive 2/3. My y-intercept is 0. So this one is going to go through the origin. My slope's positive, so we're going to move uphill as we move from left to right. We're going to go vertically by 2 to horizontally by 3. So that puts me right about there. Let's do another point this way also. So we should end up right about here, and I'm going to draw a dashed line because since I have a strict inequality, in other words, I have greater than, I do not have greater than or equal, that means the boundary will not be included. Okay, so now I need to choose a test point that's not on the line. For many lines, the origin is a good test point because 0, 0 makes all the arithmetic very simple. However, here the origin is actually on my line, so I can't use that one. I'm going to use instead something that's also pretty simple. Let's use 1, 0. So now we're going to put our x equals 1, y equals 0 into our original inequality, which is 2x greater than 3y. This gives me 2 times 1 greater than 3 times 0, 2 greater than 0. Is this a true equation? Sorry, a true inequality? Yes, this is true. So that means I'm going to shade the half that contains that test point. Okay, and here's my 1, 0. I really should put a scale on this anyway. Here's my 1, 0. So because I got a true statement, that means I want 1, 0 to be shaded, and so I'm going to shade everything down here. That's how we graph that inequality. Now we're going to move on to systems of linear inequalities. We want to find the graph of all the ordered pairs that satisfy all of the inequalities in the system. We're going to call this the solution region. And it's going to be a shaded area. In other words, we're going to have an infinite number of points that satisfy all the inequalities, at least in most cases. And so we are going to have a shaded area that we call the solution region or the feasible region. What we'll do is we'll find the shaded areas for all of our individual inequalities, and then we'll determine which area satisfies all of them. And we'll also talk about corner points, which are the points in the solution region that are at the intersection of two boundary lines. Let's look at this system. Now, the first thing that we need to do is we need to graph the lines associated with each of these inequalities. We could convert them to slope-intercept form and find the slope and the y-intercept. However, it turns out that when we're actually using these linear inequalities to solve problems, that it's useful to have both the x and the y-intercepts, and that will also be a quicker way for us to graph it. So if we look first at x minus 2y equals 6, the first thing we do is we want to find the y-intercept. How do we do that? We're going to set our x equal to 0, and so now I get 0 minus 2y equals 6. Divide both sides by -2, and so then my y is equal to -3, and this gives me the point 0, -3. Then we'll find the x-intercept. And to do that, we will set y equal to 0. And so now I get x minus 2 times 0 is equal to 6. And so that tells me that my x is 6. And so this gives me the point 6, 0. If I put a scale on my graph on each axis, okay, and I go out to 6, 0, make that one a little bit longer. So now I have a point right here, and I have a point at 0, -3. Okay, this first line will be a dotted line because we have a strict inequality. Strict means that equality is not allowed. We don't have an equal sign combined with our less than or greater than sign. And so we draw a dashed line, boundary not included. And now we move to our second line. So now we have 2x plus y equals 4. Now let's see if we can expedite this so we don't have to write so much work. We will go through the same thought process. Here's what I'll do. I will think of setting my x equal to 0. I'm just going to try to write down only the ordered pair. So if I set my x equal to 0, it means I can think of covering up this term, and so what's left? Y equals 4, right? So then I get 0, 4. Now we're going to think of setting our y equal to 0. So go back to your original inequality and just think of covering up your y. So now what do we have? Now we have 2x equals 4. We can solve that in our head and get x equals 2. In other words, we go through the same process, but we don't have to write so much once we get the hang of it. Hopefully that tip will help you. So we know this one will go through the points 0, 4. So there's 0, 4, 2, 0. This will be a solid line because of this inequality sign here. Equality is allowed. So we draw our line. It's going to look, whoops, sorry, I just drew it through in completely the wrong place. Let's try that again. I was looking at the wrong dot. That's better. Okay, so that's our second line. Now we need to do the shading. So first, if we look at x minus 2y less than 6, let's choose for our test point the origin, 0, 0, because it's not on the line. So if I put this in, I get 0 minus 2 times 0 less than 6. So we get 0 less than 6. You'll see why we chose this. It makes the arithmetic very simple. This gives me a true statement, which means I'm going to shade the half that contains the origin. We can think of shading toward the point 0, 0. Okay, so we think of shading toward 0, 0. So here's my 0, 0. So that means I'm going to shade this way. Sometimes I'll just do it with arrows. And when you get a whole bunch of them, you'll probably find this helpful to you. Or if you want, you can just shade the whole thing. You just want to make sure you don't get your shading confused with all your other lines. Now let's look at the second inequality. 2x plus y greater than or equal to 4. Once again, if we put in as our test point the origin 0, 0, now we have 2 times 0 plus 0 greater than or equal to 4. So we get 0 greater than or equal to 4. This is a false statement. So that means I want to shade the half that does not contain the origin. So here I'm going to shade away from 0, 0. Here's my 0, 0. Here's my line that these came from. So I'm going to shade this way, away from it. And so sometimes you can use the arrows. And so when you look at all your arrows for all your lines, you can figure out what area satisfies them all. I'm going to go ahead and this time go ahead and shade, and I'm making my shading go in a different direction than I did before. Now what you want to do is look to see what area is shaded for all of your inequalities. If I look over here in this area that contains the origin, in this area I only satisfy one of the inequalities. If I go down below, right here, then I don't satisfy either of them. Over here I satisfy only the second inequality. It's this very top area that satisfies both. And so I'm going to shade that. And you want to make it real clear. Don't make the reader interpret all your crazy hash marks that are going all kinds of different ways. We're going to shade this very clearly in another color. And we're going to make sure that the boundaries are also clear. Okay. Now what we need to do is find the corner points. These are going to be at the intersections of the boundaries. And actually, I'm going to go ahead and find this corner point, but I want you to notice that this corner point, while we still call it a corner point, at least in many cases, this is actually not in our feasible region because it is on that boundary, that dashed line, that is not included. But it's still often important to be able to find the coordinates of that point. Even though it's not in our feasible region, it is adjoining our feasible region. So we're going to go ahead and do it. So to find that corner point, I'm going to write down the equations of both of those lines. So I have x minus 2y equals 6, and I have 2x plus y equals 4. So you can do substitution or elimination. You could even do matrices if you want. I think it'll be more straightforward to use substitution or elimination. I'm going to multiply this second equation by 2, and that will give me 4x plus 2y equals 8. Rewrite my first one, x minus 2y equals 6. If I add my equations, then I'm going to get 5x equals 14. So my x is equal to 14 fifths. And when we're looking at graphs, it's usually helpful to write this as a mixed number. So this will be 2 and 4 fifths. And that way you can look at your graph and see if that seems reasonable, which I think it does. Now we need to find the y coordinate. You could plug 14 fifths into one of your others, or you can just do elimination on the other variable. I think that will be easier. So I go back to my system, x minus 2y equals 6, 2x plus y equals 4. This time I'm going to multiply the first one by negative 2 and leave the second one alone, this will give me negative 2x plus 4y equals negative 12. Here I still have 2x plus y equals 4. If I add these, I'm going to get 5y equals negative 8. So my y is equal to negative 8/5, or negative 1 3/5. So our corner point then is, let's write it, we can write it several ways. We can write 14/5 negative 8/5, or we could write it in mixed numbers, which would give me 2 4/5 negative 1 3/5. Or we could write it as a decimal, which would give me 2.8 negative 1.6. Any of these ways is just fine. And before you trust it, make sure you go back to your graph, look, and see if that answer seems reasonable. Let's go back to our graph. 2 4/5 negative 1 3/5. I think that seems reasonable. I'm a little bit off in my scale and my lines, but it certainly seems reasonable. You always want to look to see if your answer seems to make sense with the graph. If it doesn't, you probably made an arithmetic mistake somewhere.